Hi all, back for another round of physics. And as promised, I said, hey, why don't we go ahead and do a little bit more in terms of circular motion problems. So to pull one up here, I've grabbed this one. I always like this one, both because it helps get some ideas about circular motion, but also it will lead into some ideas about angular momentum later. And that to be continued, but I always like this problem. So here's a variant of it. A mass m is moving in a circle of radius r on a frictionless surface. Attach the mass as a string, which runs through a hole in the surface to a hanging mass of big M. So I've got two masses here. I've got little m on the surface. I've got a hanging mass big M. And what is the speed of mass, the little mass, so that it remains in a stable orbit? So in other words, let me go ahead and draw a picture for you. We have a hanging mass big M. We have a small mass little m, and little m is moving around in a circle, right? Circle on the top of this table. Okay. And we're told the circle radius is r. So this distance is r. And we're asked to find the speed. What speed does mass m travel at? So let's go at this. So we have two parts. Basically, step one is find the tension. We need to find tension in the rope. And then after that, then we can find the speed. Okay. So let's go ahead. In order to find the tension, what's a good choice of system? And what's a good choice of surroundings? Okay. So the system, I would say the hanging box, so big M. And in the surroundings, I would say the rope and the earth. So the rope is the tension force, or the tension force. And the earth is the gravitational force. And we'll use little g here. We'll say we're close to the surface of the earth. And so we go ahead. Why don't we call this direction positive? We'll call... For the first part, we'll call that positive. Okay. And so we go down and we start thinking about applying our relationship. Our Newton's second law, F net is equal to ma. Okay. And in this case, we just need to deal with the y direction. And so here we have the net force in the y direction is equal to our mass times our acceleration in the y direction. Now looking at, okay, well, we better do a free body diagram. So we say, okay, well, here's Fg. And because we're talking about a stable orbit, that means that my tension force better be the same as my gravitational force. So we go ahead, Ft minus our gravitational force. And again, the stable orbit means that my acceleration should be 0. So we get something that says Ft is equal to the force of gravity. And of course, substituting in our actual definition for the gravitational force, we end up with mg. I assume that. Okay. So we're buzzing through this a little faster now. You've got a lot more experience with it. So let's go ahead and now let's address our step 2. So the idea of a system and surroundings for step 2. Yeah, okay, so we're talking box M. And in the surroundings, we have the rope, which is the tension force. We have earth, which is the force of gravity. And we have the surface, which provides a normal force. Excuse me, notation. Let's say F of n. Good. So let's go ahead and do a free body diagram now for little m. And I'll say that it's... Okay, so here's little m. I'll say that we're positioned such that the tension force is exactly to the left. So we'll call this Ft. And of course, we have our normal force up, Fn, and we have our gravitational force down, Fg. Now here's one thing that I'll point out, okay? And I'm going to choose an axis system, but this time, it's rather than choosing, to the right or to the left or, the usual kind of system, like our X, Y, and Z, I'm going to choose a different coordinate. And I'm going to say that I'm going to call the positive direction, we'll call the positive direction radially inward. Okay. So this takes a bit of stretching, but the idea is that if I call the positive direction radially inward, you can think that, okay, what does this mean? It means that as the box moves, the coordinate system is also moving, right? The coordinate system moves, rotates, so that radially inward is always pointing towards the center of the circle. Okay. Now that's perfectly valid. It helps sometimes with conceptualization, but for example, of moving objects. So if I call my radially inward always towards the center of the circle, then it just makes life a little bit easier in terms of thinking about positive directions. Okay. So if I call the positive direction radially inward, and generally the other direction that you'll think about is parallel to the motion. So radially inward, this would be the perpendicular component, and then you have a parallel component, say the direction of the velocity, and those two are always perpendicular to one another. So this parallel and perpendicular set up another interesting coordinate system, one that's not stationary in space, like what we've been used to dealing with, but rather one that's set up so that it can rotate in space. So if I call it radially inward, okay, well, let's go ahead and apply our physical principle. F net equals ma. Okay. And now here we're going to take the radial direction. Radial direction. Okay. And hopefully now you see where the value is and actually saying positive is radially inward. So now looking at the radial direction, we have our tension force, which is always radially inward, so I put a positive in there, equals our mass times our acceleration. And again, note I have a positive sign here because the acceleration is always towards the center of the circle, again, in the positive direction. So that makes life a lot easier. Okay. Well, let's go ahead. And we have an expression for the tension force from the previous problem. Remember that the tension force was equal to our mass times our gravity, our big M. So I'll go ahead and substitute that in, big M times G. Over here, this is truly the mass of the little mass, so we'll leave this as little m. And I'll substitute in our definition for the centripetal acceleration. We're told that we're moving in a stable orbit, a circle. So we go ahead, we do a little bit of magic. We get mass over gravity times r divided by little m is equal to our speed. I'll take the square root here. And this should make some intuitive sense. The larger the hanging mass, so we're going into sanity checks here, but the larger the hanging mass, the faster the little mass should go in order to support that hanging mass. Or for example, if the radius is larger and the mass stays the same, you would think that, okay, it has to cover more distance, and so again, it should have to go faster. Okay. Smaller mass, smaller little m. Okay, again, the thing has to go faster. So this does make some intuitive sense. Okay. So we have this value. We have, I'll say, okay, we have the sucker. And let's go ahead and move that. I've got another question for you, so let's go ahead and move this result. We'll move it to a more convenient location, right here. Okay? Cool. So here's the next question. And yes, indeed, you can do this. You're probably familiar with this, but yeah, you can do this in order to keep a hanging object, right? You just have to move the other object really, really fast. Okay? So now here's the next question. If we go ahead, let's get rid of that. Say for a moment, if we double m, what is r? Question mark. Okay, so we'll go ahead. If we double the mass, the hanging mass, what's the new radius, the new orbital radius for r? So say, take a second, think through that, see if you can come up with an answer. Okay, you got it? Okay. Well, let's go at it. So I'll call this r old, is what I'll do. I'll call this distance the old distance, and then we have a new one. So let's go ahead and set everything up. We have fnet is equal to ma. And again, taking the radial direction, we have our tension force, Ft, is equal to m times v squared over r. And I'll call this one r final. Okay. Over here now, remember we doubled the mass, so we have 2mg equals m over r final. And I'll go ahead and substitute in my expression that I had originally. We had mg times r initial over m. Oh, goody goody. Now we get to cancel everything, right? We get little m cancels little m, big M cancels big M, G cancels G. And I end up with this cute expression. I get an expression that says my final, if I do this kind of rigmarole transfer, is exactly half of my initial. So if I double the mass, I end up, if I could just instantaneously double the mass and let it settle back into a stable orbit, you'd see that, hey, my final is half of my initial. Pretty cool. Okay, well, that's enough of that. Let's go ahead and let's trash all of this stuff. Trash. There we go. Let's trash all that. Let's go for another problem. Let me get it up here and I'll be right back. And we're back. Let's go ahead. So another circular motion problem here. And pulled this one out. The Full Throttle Roller Coaster, Six Flags Magic Mountain, California, has a vertical loop. How fast must the roller coaster be moving at the top of the loop such that the cart does not lose contact with the rails? Okay, so we're first of all, let's be careful. We've got a verbal clue here. Cart does not lose contact with the rails. So we're looking for that boundary point right between it's in contact and it's not in contact. Okay, so there's that boundary point there. For the roller coaster lovers in ya, there's a picture of it. Okay, so we're looking at vertical loop. And I should also say that this vertical loop is about 49 meters. Okay, so 49 meters in diameter, I believe it is. Yeah, I think it's 49 meters. So let's go ahead and we'll draw that in right here. We'll say, okay, this distance from here to here is 49 meters. Okay, so it's rather large. Okie dokie. Well, let's get some ideas about how do we actually approach this problem. So go ahead, plan out your steps. You got it? Good. Well, actually, I think there's just one step. step, just one. We can find it, find v. So I don't think we have to go any further than that. So let's go ahead. Let's get an idea. System and surroundings. You got it? I think here the best would be the cart, and we'll say the earth. Here for the surroundings is the force of gravity. And track. We'll call that the normal force, Fn. Okay. Well, let's go ahead. Set up a coordinate system. That's always good. I'll call up positive here. And let's do our free body diagram. Wham! There's our cart. And okay, we have our force of gravity going downwards, Fg. And here's the other interesting one. So this comes back to does not lose contact with the rails. If I'm thinking about this verbal hint, and I'm thinking about that boundary between contact and not contact, the question then becomes, what's the normal force? Hopefully you see that if we're right at that boundary where it's not in contact anymore, that we actually don't have a normal force. So maybe I get a little overzealous here. We don't actually have a normal force in this case. So we'll get rid of that. So all we're dealing with here is the force of gravity. Cool. Let's go ahead and apply Newton's second law. And I'm going to look at the y direction, dir. Okay. And so we end up with something that says F net equals ma in the y direction. Now the next question. Okay. Okay. Now let's go ahead and substitute in our definitions for whatever forces we have. I mean, well, the force we have is the gravitational force. So I should probably do that, AY. And now, go ahead and I'll move over. Now let's substitute in our definitions. We have the mass of the cart times gravity. That's the definition for the gravitational force. And I have the centripetal acceleration, v squared over r. And let's keep in mind, both of these are in the negative y direction. I called positive up, which means these are both downwards. Oh, goody, goody. We see right away, hey, the mass of my roller coaster doesn't actually matter. Sweet. That's number one. And so, and of course our negative signs cancel. And so we end up with something that says, hey, g times r is equal to v squared. Or, guess we could plug in some actual values, 9.8 times 49 over 2 square rooted equals v. Well, let's go ahead. I got to think about this for a second because 49 over 2 is about 25. 25 times 9.8, so that's about 250. So whatever the square root of 250 is, let's see. It's going to be about 16. Okay, so you go ahead and plug that into your calculator, but it's just going to be a shade under 16. I'm guessing it's going to be something like 15.8 meters per second equals v. I say, again, go ahead and plug that into your calculator, actually get the right value. But just ballpark-ish, you know that 15 squared is 225. 16 squared is 256. And so we're going to be just a shade under 16. Okay. Cool. Thanks for your attention. Have a good afternoon.